So let me start my discussion on the bridge design using the parametric approach rather than the traditional approach. So it combines the bridge language with the definition which is parametrically handled. So let's see what that is. So if you look at a bridge project, actually bridge project is a pretty wide subject because you deal with structural forms, you have many materials, you have to look at the life cycle steps, you look at the construction methods, analysis methods, use of the bridge, pedestrian or a canal bridge or a waterway bridge or a flyover. You look at the components of the bridge and so on. So the bridge has a very broad spectrum, and that's what makes it more interesting and also challenging. But let's focus on one of them at the moment, and that is the components of the bridge, because if you expand everything, we can go into many ways and very deep. But if you look at just the components, you will have primarily the layout components, and you will have the substructure components, and then you will have the superstructure components. And superstructure has further many components, deck slab and so on. Substructure has further components, and layout normally has vertical and horizontal alignment. So we put all these components together, then we make a bridge. So if you are going to do the modeling, these components and this language of the bridge needs to be handled. So today we are only talking about a very specific type of bridge as a simplest form to begin the discussion. So we're talking about a typical concrete precast I-Girder bridge, which will look something like that. So you have the components in that way. And we are going to look at how we can efficiently model, design, analyze, and design, and also make an efficient bridge. So it's not about efficiency of the modeling process, but also efficiency of the structure itself that we'll be looking at. So if I take this bridge, and then if I look at it, we can actually explode this bridge like assembly. So bridge is more like an assembly of components. So each component is individually completely defined by itself, and then it can be assembled together by using the relationship between each other. And here you can see each component of the bridge, exploded view, and then you can bring them together. And then the process of defining each component and the same components can be used for another type of bridge, like for example, flyover. So if you look at the flyover, same components are rearranged in alignment, vertical alignment with varying height, varying things, but basic components are the same. And this is what we are talking about, that bridge is a component-based design where each component is defined and then they are assembled based on certain rules, which are typically coming from the alignment. So having that capability with us to define a bridge using its components also gives us the capability to integrate the design process. That means now we can integrate the entire design process because we have defined the components in a systematic parametric form. So in this case, we are going to talk about two programs. One is the CSiBridge main, which was first released in something like 2004, 20 years ago. And that is a general program, actually is based on SAP 2000, but it specifically handles bridges. And now very recently, we are now talking about, after almost 20 years, we are talking about CSiBridge Express, which is a kind of a sister program, gradually adding more functionality to the main program. And we are going to focus on this program today for the demonstration and for the discussion. So let's go further. So if I look at the CSiBridge, the bridge project in a CSiBridge program can start from the layout on the terrain, for example, Google Map or something. And from that terrain, we build up the bridge, and we will show you how to do that later. And from that, we create the finite element, mesh automatically. Then from that, you run the analysis automatically. You get the results, extract the results, and get them back to forces. And then from there, you design the component. For example, here is a capping beam design. And then you design the columns. Then you design the section reinforcement. And then you can generate the whole reinforcement cage after the design. And then that can be transferred to Revit or IFC or other programs. And that can also be transferred to the main CSiBridge, like I mentioned to you, for further refined analysis. You can also use virtual reality to view that. You can generate BOQs cost estimates and everything from there. And then finally, you can transfer it back to Google Map to see how it will look like. So that's the full integrated process. But the interesting thing is that from the design, we can also go directly to the design calculation, from there to BOQ and go back. This shortcut provides us a great opportunity where actually the BOQ can be generated directly from the parametric model without going through the design process, and then just simply update later. And that's what we're talking about, the design efficiency and structure efficiency quickly. Because the parametric model is complete or at the beginning, so we are not waiting for other process to complete before we get the information. So, like I said, we can go shortcut from that to the BOQs, and then we can update it after the design is completed. So this integrated process where you can move to different steps in between without completing the process is a great advantage when we do the preliminary design of the bridges or we look at the efficiency of the systems. So what is parametric modeling? Parametric modeling is basically a way to define things in terms of variables, fixed parameters or primary variables, and some derived variables or variables that can be computed from the fixed or initial parameters, establish relationship with them, and use these for creating the computational model, geometric model, and everything. And this is a very different approach than making everything one by one, when each element is independently defined and have no relationship with each other, which is the traditional finite element modeling that we use. So there are many programs currently available for doing parametric modeling, for example, Rhino, ArchiCAD, Revit, Dynamo, and those can be, and Grasshopper and many. So many people are using them. So you can create a parametric flow of the parameters you can create, and you can link these parametric models to program like SAP or other to do the whole thing, and you can put them into a loop. But this requires engineers to learn parametric modeling, learn Grasshopper or Rhino or Revit or Dynamo, and learn a little bit of programming. So what we are looking at is putting this functionality directly into a tool. For example, I give you a quick example how this parametric model will work, where you define the parameters, you link them together, and once you change any parameter, then the structure is updated quickly and completely by changing just one parameter. So you can change the weight, everything automatically adjusts. We change the length, everything adjusts. This capability of parametric modeling, parametric editing based on this flow gives us a great power to create very complex, comprehensive, but geometrically complete, consistent models. So this approach is now put in CSiBridge internally so that we don't need to do the modeling, the programming by ourselves. The program already has this built-in capability to do that. So this is, for example, a full parametric model of the bridge. You can see here that on the left-hand side are the components of the bridge, and the middle side you can define the properties of the components or the relationship between components, and the right-hand side shows you the graphical representation of the geometric model. And this is as complete as a physical bridge typically is. And once you change one parameter, everything gets updated automatically, and bridge remains connected to each other. So this is how the parametric model will work. For example, here you can see the components. Components have parameters. Parameters have parameter relationship, and then they have geometry. And for example, this is a straight bridge that I made. If I now change the alignment to a curved one, all the components will automatically realign themselves to the curved component without making any change. So because parametrically they are linked together. If I change the slope, the column height changes and the wall height changes to follow the vertical alignment. This parametric modeling is the key to creating the models quickly. For example, if the alignment changes, all we need to do is select a different alignment, and the bridge will just follow the new alignment without making any changes. And everything, the quantities, the finite element mesh, the analysis, the design, everything will be updated accordingly. So this is a great advantage over the traditional modeling, where if you change the alignment, you have to remesh, remodel, relocate everything manually. So that's the advantage that we're looking at. Now, how does that parametric model works? So first of all, can you please click this? I think this is a video. So if you look at this, this is how we can define the parameters in a girder. So if you see how we can define the girder dimensions, we can look at the cross-section, and everything is defined here. So all of the information that we need for the girder to work as a component is defined in the parameters, including its reinforcement, its properties, its tendons, and so on. So we can put all of those things inside the girder itself. Could you just forward this a little bit? Yes. Yeah, a little bit forward. So you can see here the tendons are there, the reinforcement is there. The advantage is that we can define the reinforcement and tendons even before the analysis is done, because they are part of the component. The only thing analysis can do is change their number or sizes or location, which can easily be updated through parameters. So because we defined the reinforcement and tendons as part of the definition of the girder, then we are now in a good position to update then after the design is done. If something is not passing, we just simply change those parameters and complete the modeling. So that's the advantage. So this is the definition of a typical component completely parametrically from A to Z. And once this is defined, then we put this component in the bridge. And then we can create, can you please run the video also? So we can create the libraries for these components. So you can have several libraries that you can see from here. There are some libraries for girders, there will be libraries for capping beam, there will be libraries for different components, and then we can look at each library. Now, one of the biggest advantages is that because we have a library concept, the components can be reused. If you define a component parametrically in one model, you save it in a library, and it can be opened in another bridge model and reused. So we can standardize the components across projects or across clients and so on. So and then still they can be modified if needed. So you can see from here that all of these components can be put in the library. Can you please move forward towards a little bit middle? Yeah, and then we can have the components for the deck slab, and similarly forward, more forward. Just keep moving, please. And then we have the components for the columns. We have different shapes of columns and pile caps and foundations. So each component types and subtypes are then saved as libraries, which can be like even the bearings can be saved as supports, can be saved as libraries, components which can be then reused. So like girder component types libraries, we have the girder rebars inside placed according to the size of the girder and shape of the girder. You can see here that we have shear reinforcement, tendons, everything, and then this is all customizable through parameters. We have deck section types that we can view. We have columns in the library of different shapes, different configurations, different form, straight columns, prismatic, non-prismatic, and then we have reinforcement. And like I said, the advantage is that if you change any dimension, the rebar cage immediately follows and automatically adjusts itself. So that capability makes this component reusable at all times and valid at all times. And then we can have the bend cap or the capping beam sections. We can have the foundation, different types of foundation, all the way to piles, and we can have the abutment, different types of abutment defined as components, parametrically defined. So you can have physical walls present in the bridge model, which will also be meshed for analysis, as you can see later. So each component will have the reinforcement also defined. So you can add a capping beam to 2 columns, 2 foundations, 8 piles, and you get this. And you can make any number of similar bends and save it in the library. So you have a great way to create kind of Lego pieces of your own to build up the bridge. In fact, later, Ashish might show you the real, printed, 3D printed Lego pieces of this bridge, how they can be actually used. So we have different bend types that you can create from the basic components. So basic, same column, same capping beam can be put in a number of ways to create more complex types of higher level components. And then, for example, you can have a Pier-Head like this one, which can accommodate the half girders, which can accommodate these curved bridges. As you can see here, this is a flyover where we are trying to keep the girder length the same, so we can vary the Pier-Head dimension. So there can be many things that we could do to use these components. You can also have these Y-shaped components, and those of you who are from Bangkok, they can see these bridges a lot, where we use these Y-shaped columns to basically, because normally you have 2 lanes, in between there's a small place where you can only put 1 column, and there's a 6-lane bridge on the top. In that case, you need these Y-shaped bends to accommodate that. Layout also, so layout can be also parameterized. So the layout can have parameters, for example, radius and so on, vertical and horizontal alignment, deck width, super elevation, everything is part of the parameters. So this completes the whole system from top to the bottom in one consistent manner that any change in any parameter will update the others. Even ground profile and soil profiles can be added to the parameters, and the advantage to this approach is that if you add the soil profile, the program can automatically assign the soil springs to the corresponding structural elements like piles or the abutment. So modeling of the soil becomes very easy because it's easy to find where the components are, where the soil properties should be applied. And this is very good because then soil structure interaction can be easily included as part of the analysis. You can also handle complications in the deck slope variation because of the drainage or because of the super elevation. So there are multiple ways, and because it is parametric, if you bend the deck, then everything adjusts accordingly. Bearings, height, everything can be adjusted. So many ways that the slope and cross slope as well as super elevation can be handled. And here you can see here the real bridges of this kind with half joint, which are very common to provide clearance, and you can have those half joint. And you can see from here that this is only possible because parametrically everything is connected. So if you change the deck height, the girder height will change. If you change the girder size on the 2 sides, automatically the capping beam will adjust. So this capability to alter the components to match with the geometry is only possible if everything is parametrically defined and connected. And that gives a great advantage in quick and efficient modeling of even complex arrangements. So let me show you how a full bridge model made from components can look like. So this is, we're just building up, and I'll show you various types of components within a single bridge. So this is the closed abutment wall. That's a single column bent with the sloping. Those are the girders and diaphragm of the above. We have pile cap. We have another one with the sloping column and the bent cap over there. Then next we have multiple column with the half joints and a ledge. So you have all these kinds of possibilities of the capping beam substructure as well as the deck arrangement. And you can model the barriers, the walkways, the lanes, and everything. And if the bridge bends, then the girder lengths are automatically adjusted to accommodate the curvature. And you can see here that we also have a bend without any foundation, directly the pier piles going all the way to the bend. And if you go inside the bridge, you can see how the reinforcement is laid down. And this is all parametrically defined even before you run the analysis. So because it's all there, so it can be used later for example, nonlinear analysis. If you want to do pushover analysis, the reinforcement is already there. So hinges can be extracted from them automatically. The tendons are already there. The tendon forces can be applied to the bridge automatically. So having all this information completely defined saves considerable amount of time, but more importantly, consistency. Now let's go to the important subject of structural modeling, because that's what we really are interested in. Structural modeling is actually interesting because for a bridge like this, you could create a very simple beam, a girder, with just one line and pin and roller support as a simplest representation. Or you can create it with the adjustment to accommodate for the height of the girder and the bearing. Or you can create a frame, 2D frames with the bearings and the girder height accommodated with the bearing joint. Or you can create the pile footing and pile caps below that. So you can create multiple types of structural representations of the same simple span, each will give you different results and each will be missing some important information. Or you can go to the full finite element mesh with a common, which is physically complete, and this of course will give you the best results. Normally the problem is that to create that mesh requires a considerable amount of effort. But if we have parametric modeling, then this mesh is automatically generated. We don't need to, as engineers, we don't need to do additional work to just get this mesh right away. So you can see above that you can actually get almost a physically complete finite element model. Left-hand side is a finite element model of the same structure with shells and solid representation. So the deck can be a spine model, could be an area object model, could be a shell element model. So for CSiBridge, we have chosen to go with the shell element model for the deck and other options for the other structures, which engineer Ashish will show you later. So deck meshing can be automatically done in shell elements, and then shell elements are automatically then converted to section cuts and forces. So for example, this is the girder mesh you can see from here. And you can, if you go closer, you can see how the girder is correctly modeled, correctly attached to the bearing. Bearing is correctly attached to the substructure. So when you do the analysis, you will not be losing any of the behavior in this model. And if you extrude that shell element, you get the same physical model back, including the variation in the girder section. So it looks almost exactly the same as we started with. So this kind of complete modeling is very helpful in capturing the response. Another advantage is the soil structure interaction. Because we have the physically complete model, we can just attach the links everywhere where there is soil and then transfer the soil properties to the links. These are actually linear links, but can also be converted later to nonlinear links for more sophisticated modeling of the soil structure interaction. And this is also, once again, done automatically based on the parametric definition of the soil profile. This is now a representation of the structural model of the same bridge, parametrically created, once again automatically from the parametric definitions and everything that we showed you earlier. And then you can see from here that this whole model is now geometrically consistent, complete, and it gives you the results for all kinds of load analysis, construction stage analysis, moving load analysis, temperature variation analysis, modal analysis, construction sequence analysis, because we can put the construction sequence there, as well as the pushover analysis for seismic capability or seismic capacity. Notice here that these shell analyses are automatically converted to beam forces or moments by using the section cut concept, where the integration of the stresses is done to get those forces everywhere. Whatever model we use, we ultimately get back the bending moments and shear forces that we need to design and do the design check, code design checks. So that's how the parametric model can help us to do analysis and design of all kinds of bends and structures using one consistent approach without losing any of the, I would say, without much simplification, and maintaining the physical meaning of the model. Thank you.